Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. Until the previous lecture, what we have seen is this: we have a transfer function, we have seen how we can get to a state space realization from that given transfer function. That's the first thing. We saw that this state space realization through some examples, of course, that the state space realization that we get to from this transfer function is not necessarily unique, yeah, and in fact, depending on how much knowledge or grasp we have over the system, we can actually choose our state variables accordingly in a judicious manner in some cases. So that is one of the things we've seen. What else have we seen? We've also seen that there's a way of reversing this process. By that I mean that given a state space realization, we've also seen that there is an expression for the transfer function. Even before that, we've also seen how to approach these different state space realizations. Yeah, one of the approaches we saw was to draw these wiring diagrams using these op amps which serve as integrators, and the other approach, of course, we saw a little algebraically, where we had this phase variable form of the state space representation, yeah, where we saw that the matrices were very conveniently represented or expressed in terms of the coefficients of the output and the input in the differential equation. Yeah, so we are fairly comfortable with these things, but before we get a bit too comfortable, let me point out one limitation of this state space method. Yeah, it will be more evident as we go into a solution of this system of differential equations, but remember that in an ordinary differential equation such as this, so here goes, a1 y double dot plus a2 y dot plus a3 y is equal to, let's say, b1 u double dot plus b2 u dot plus b3 u. Yeah, so I can give you a ordinary differential equation like this, where I tell you the initial condition at, let's say, y0 is equal to, say, some p, the derivative of y at some other instant of time. So for example, let's say y2 is equal to q, y dot of 2 rather, not dash, let me not mix up the notation. So y dot of 2 is equal to q, and y double dot at, let's say, 5 is equal to r. Yeah, you should be able to solve this differential equation, right? But unfortunately, this cannot be solved by setting it up on an analog computer. By an analog computer, what I mean is basically those banks of integrators or op amps. Yeah, so for the state space method to work, you need to know y naught, y dot naught, and y double dot naught, by which I mean that y dot and y double dot at the same initial instant. Yeah, you cannot have knowledge about y at some instant, knowledge about y dot at some other instant, and knowledge about y double dot at some other instant and expect to solve it using the standard state space technique. Yeah, so that is one limitation. So as I promised you some time back, so here goes the first warning. So this is a limitation of the state space setup that we are going to work with. Okay, so don't expect to solve this kind of differential equation using the conventional state space method. It doesn't work that way. Okay, Alright, so enough said. So what we haven't seen so much of is maybe some examples. We have seen in principle that given a state space representation we can go back to this transfer function, but unless you try out with an example you might be misled into thinking that it is very simple and that the computations are really child's play. However, you might soon be surprised when you are dealing with a real system maybe of even 4 cross 4, right. So when there is a 4th degree differential equation, and you will see that the computation can be pretty laborious in general. So just to give you an idea about the kind of computation that it involves, here is what I am going to do. I am going to take a couple of examples where I am going to give you the state space representation, and then we are going to compute this transfer function. So this is the standard state space representation. Of course, we are also making allowances for the feed forward, that is this du term, and let us say A is given by 0 1 0 0 0 1 minus 1 minus 2 minus 3, and suppose B is given by 1 0 0 and C is given by the transpose of that, 1 0 0, and D is 0. Okay. So the question is to obtain G of S, the transfer function, which is given by C times Si minus A inverse B plus D. Alright, this is what we are required to obtain. So how do we go about this? You might ask, how do we go about this? Okay, so let's try to cut to the chase and get ourselves going. So what is the first thing we do? The first thing we do is, what is Si minus A? So let me copy that from the previous slide so I can write it. So of course S minus 1 0, so you can check if you are doing this calculation along with me, you can keep checking as I am carrying on with these steps. Then you have 0 S minus 1, 0 S minus 1, and finally 1 2 S plus 3, because remember there is a minus sign sitting in front of A, so the signs have changed, right. So what we essentially want to do is we want to find the inverse of this. The moment we want to find inverse of something, it is generally not a very straightforward calculation. So the inverse of this is going to be the adjugate of this Si minus A divided by the determinant of Si minus A. What is the adjugate? The adjugate is the transpose of the matrix of cofactors. Of course, if you are finding this a little confusing, I urge you to go back to some basic matrix theory or linear algebra lessons where you have these definitions of the inverses of matrices. What I am trying to say here is that now you have this S and all, it is not just numbers, so computing these inverses you have to do it in a symbolical manner, right. You have to carry the symbol S. So it is not going to be very straightforward as expected. So what is determinant of this? Let me just do that computation. So I am going to do the Laplace's expansion of this determinant. So the determinant of Si minus A is given by S times S into S plus 3 plus 2, just check the calculations, plus, so this is minus 1, so minus of minus 1, because this is 1 2th entry, so 1 plus 2 is 3, so this sign reverses, so it is plus 1 times 0 into S plus 3, 0 into S plus 3 plus 1, so this in times this minus this times this, so this is plus 1, So what we have then is S times S squared plus 3S plus 2, plus just this 1 here, that gives us S cubed plus 3S squared plus 2S plus 1. So we already have this determinant evaluated. Now what is this adjugate? So it is a matrix of the transpose of the matrix of cofactors. So what is the cofactor of S? Cofactor of S is S into S plus 3 plus 2, yeah. So I will have S into S plus 3 plus 2, that is the 1 1 entry. What is the cofactor of this? 0 into this minus this, so that is plus 1, but of course the same sign will change, so it will become minus 1. What is the cofactor of this? 0 into 2 minus S, so it is going to be minus S, yeah, I hope I am not making a mistake. Then what about this? It will be 2S plus 1, I guess, yeah, 2S plus 1. Of course the sign will change, so it's, hang on, let me do the computation, S into 2 plus 1, so 2S plus 1, so it's with a minus sign, yeah, yeah, so this is 0 into S plus 3 plus 1, yeah, I think I am not making a mistake, hopefully, yeah, even if so, then you are going to correct me, yeah. What about this? S squared, so this is going to be S squared. Of course I believe that the sign will not change for this, because it's, yeah, sign will not change for this. What about this? It's minus S minus 0, so the sign will change here, so it's going to become plus S. What about this entry? It's going to be 1, and the sign is going to change, so it's going to be minus 1. What about this 0 that's sitting over here? It's going to be minus, so hang on, what about this term? It was minus, it was 1, no, the sign won't change, I am sorry about that, this sign won't change because it's a 1/3 entry, so it's going to remain as it is, so it's going to be plus 1. I suppose this one sign, yeah, this one sign changed, this one sign didn't change. What about this? This is going to be minus of S plus 3, but then the sign changes, so it becomes S plus 3. What about the middle term? Well, of course the sign will not change here, so it's going to be S into S plus 3, S into S plus 3, but then the transpose of this, yeah, this is going to be the adjugate of Si minus A, yeah. Anyway, please check these calculations, but you already see that it's going to be a pretty laborious process, right? At least that I hope you are able to appreciate, which is all the more reason for you to practice more and more problems of this nature. Otherwise, you know, if you are appearing for an exam and you want to solve this in quick time, unless you have practiced this well enough, even if you know everything, you will still not be able to finish in time, and worse still, you will probably get the calculations wrong and lose out, yeah. So please practice this, that's probably a humbling lesson. So this is going to be basically S squared plus 3S plus 2 minus 1 minus S, then S plus 3, S squared plus 3S, and minus 2S minus 1, and finally it's going to be 1S S squared, whole thing divided by this determinant that I had obtained, S cube plus 3S squared plus 2S plus 1, yeah. This whole thing that I have obtained here, I believe that's what it's going to be. So this is equal to, so finally one whole slide it took me to get this Si minus A inverse. Now once I have obtained this Si minus A inverse, what I have to do is I have to pre-multiply by C and post-multiply by B. I don't need to bother with D, because in this case the D is given to be 0, yeah. So what's my C? C is basically 1 0 0 and 1 0. So let me just quickly multiply that. So then 1 0 0 times Si minus A inverse times 1 0 0. So recall that this is C and this is B. So what is this going to be equal to? Well, I can clearly see that when I pre-multiply by this, it's going to just pick out the first row of this matrix, yeah. Pre-multiplications are generally acting on the rows of a matrix. When a vector pre-multiplies a matrix, a row vector pre-multiplies a square matrix, you will do well to remember that this is just taking combinations of the rows. So this is 1 times the first row, 0 times the second row, 0 times the third row. So basically it is selecting the first row, that is what this matrix is doing, this C matrix. So then once I have multiplied this, I am just selecting this first row. So this is going to be nothing but first row is s squared plus 3s plus 2 plus 3s plus 2, the second entry I believe was s plus 3 and the third entry was 1. Let me just check and be sure, yeah, I am correct. So then, and finally this, you could have also looked at it from this manner, that this post multiplier is actually going to pick out the column. So basically the action of these two is to pick out the first row of this matrix and the first column of this matrix. This B vector is picking out the first column of this matrix. So the combined effect is to pick out the 1/1th entry, the element in the first row and first column, which is nothing but, just this. So in this case, because of the beautiful structure of B and C, at least I am saved some trouble. Yeah, I didn't have to add these fellows. I am just selecting one fellow and that's it. So therefore you see that this GS comes out to be, oh of course I have to still write that determinant Si minus A, yeah, I shouldn't miss that. So I didn't, because of want of space I didn't write that whole cubic expression here. So this is going to be basically nothing but s squared plus 3s plus 2 divided by whatever was the determinant, s cubed plus 3s squared plus 2s, s cubed plus 3s squared plus 2s plus I believe it was 1, yeah it was 1. So that is the transfer function. We have done it, right. So we started with a given ABCD matrices, a set of ABCD matrices, and we have obtained the transfer function. Let us do another example to sort of warm up a bit. So let us take a second example, again a 3 by 3. Yeah, most often you see you go beyond 3 by 3 and things become very, very difficult for hand computation. That is why you need MATLAB. So now I am not giving a very nice structure to this A matrix, I am just going to give it this kind of arbitrary structure in some sense. Yeah, the B matrix is still this 0 1 1, so no nice structure as such. Yeah, this could very well be a state space representation for all I know. Yeah, 1 0 0, and again the feed forward, as I said, often you will see that this feed forward is not there. At this point, just before we get into this example, let me just mention something. A while back when we were discussing these controller synthesis and design problems, if you recall I had mentioned this briefly, that this PID controller cannot be realized in the state space form, and I had told you, I had promised to you that when we do state space I will actually explain the reason behind it. Now it should be very obvious to you. You see, with this form of state space representation that is given by this, yeah, the most you can get to is a biproper transfer function, right, because you see now you will think about it a bit, it does not take a long time to think, maybe a rigorous proof will take some writing to do, but you see this matrix Si minus A, yeah, when you take its determinant, how many S's are appearing, every column and every row has one S. So when you take the determinant, if it is an n cross n matrix, the determinant of that will be a polynomial of degree n, not just a polynomial, it will be a monic polynomial. What I mean by a monic polynomial, I have explained this earlier also. What I mean by a monic polynomial is that the coefficient of the highest degree is unity, and indeed we found it to be so. So here you see this coefficient is indeed unity for s cubed, which is the highest degree, right. So this is also called the characteristic polynomial of a matrix. Yeah, if you take a matrix A and you find out the determinant of Si minus A, where S is the variable, then this determinant Si minus A is called the characteristic polynomial. In fact, possibly MATLAB has a command something like char poly. Yeah, please do check. I am not very sure about the syntax, but you should definitely check these out on MATLAB. Yeah, so this has got a name in linear algebra, and also in a few lectures we shall be using a good result about this characteristic polynomial, which is a result due to Cayley-Hamilton theorem. It is known as Cayley-Hamilton theorem, which says that if you replace this variable S with the matrix A itself in this expression, that is determinant of Si minus A, yeah, you will end up satisfying this equation. And of course do not fall into the trap of seeing that, oh that is obvious, because you know what, we are going to put this, replace this S with an A here and it is going to become A minus A and determinant A minus A is 0. No, that is a fake proof. Yeah, that is a very, very, very fake proof, very tempting to imagine that that's how the proof works, but that's not how the proof works. Okay, that's not no matter who might tell you what, that's not a simplified proof of Cayley-Hamilton theorem. In fact, it's no proof at all, because remember, a determinant is going to be a scalar after all, right? So this ai minus a, yeah, is not the same as this determinant. So don't fall into that trap of thinking that, yeah, I have a very easy proof of Cayley-Hamilton theorem. No, that's not how it works. Anyway, so what I'm saying is this, we are coming back, I was digressing a bit. So coming back to the main point on hand, you see what you have here is this determinant which is sitting in the denominator, which is the common denominator of every term in this Si minus A inverse matrix. Yeah. Now think about this. What is this adjugate of Si minus A? This adjugate of Si minus A has entries such that every entry is a determinant of a 2 by 2 block in this case. In the n by n case, the determinant is an nth degree polynomial, right? But every entry in the adjugate, what is the highest possible degree in terms of S? It cannot be more than n minus 1, I am sorry. Yeah. So for example, here you see in this light of this example, this is a quadratic polynomial, this is a quadratic polynomial, the rest are not even quadratic. This is a first degree polynomial, linear polynomial, this is just a constant polynomial. Yeah. So this is not surprising. Why is this not surprising? Think of how we are evaluating the adjugate. We are just, if we are trying to take the adjugate of this matrix, we are just trying to find out the A11th entry. So we are just taking out this A11th entries, the corresponding, the corresponding row and column for that entry. So when we are finding out for A11, we are taking out this particular row and we are taking out this particular column and finding out the determinant of the remaining n minus 1 cross n minus 1 block. So what can be the highest degree of that n minus 1 cross n minus block? After all, it has only, yeah, I mean this original matrix, that is. So I am basically talking about this. Yeah, so you are trying to find out the A11th entry of this adjugate. So you take out this particular row and you take out this particular column, and then you are evaluating basically the determinant of, let me mark it with a different color. So you are basically evaluating the determinant of this block, and this block cannot have a determinant whose degree in S is greater than 2. Yeah. So every entry in that adjugate sitting over there, yeah, cannot have degree greater than n minus 1. What does that tell us? Now see, if you write down this Si minus A inverse at its determinant, which is the denominator polynomial, is going to be of degree n, and the highest degree of any entry in that adjugate matrix, adjugate Si minus A, is n minus 1. So if I had pushed this, let us say if I had pushed this term inside, you would have seen that each entry of this Si minus A inverse would have been a rational function, ratio of two polynomials. The numerator polynomial would have a degree strictly less than the denominator polynomial. Okay. So that is for Si minus A inverse. Next step is what? Next step is, I am going to pick out this, remember the C and B matrices are just constant matrices, no S is involved in these, right. So they are not adding any S or dividing by S anywhere. So what is the C doing? C is just basically telling you to take linear combinations of the rows of this Si minus A inverse matrix. Yeah, as I have just explained. Here of course it is just selecting the first row. If I had 1, 2, 3, then that would be 1 times the first row plus 2 times the second row plus 3 times the third row. But if you add rational polynomials, yeah, and each of those add rational functions, and each of those functions has a common denominator, yeah, and each of those, so for example, let's explain this a bit. So you have n1s upon ds plus n2s, or rather a1, or should I say alpha 1 n1s upon ds plus alpha 2 n2s upon ds plus so on and so forth, alpha k nks upon ds. So the ds is common. Why is the ds common? Because in this case the ds is basically the characteristic polynomial. Now if you are adding terms like these, that is basically what this C is suggesting you to do. Yeah, every entry of this Si minus A inverse when pre-multiplied by the C matrix is going to be a row matrix now, a row vector. It is going to have the same shape as the C matrix. Once you have pre-multiplied this Si minus A inverse by C, the shape of the resultant C times Si minus A inverse is going to look exactly like the shape of the C matrix. Why? Because this is 1 cross n, this is n cross n, so the product of those two matrices will give you 1 cross n back again. So what is each entry of those 1 cross n vector, that row vector? Each entry looks something like this, where the degree of each of these n1, n2, n3 is strictly less than the degree of D. So then the resultant sum, what can its relative degree be? Yeah, you see, you take summation, so basically this is going to be like summation alpha I nis upon ds, but each ni is restricted to be of maximum degree n minus 1. So the summation of alpha I ni cannot be any degree greater than n minus 1. So this resultant sitting in this C times Si minus A inverse, this C times Si minus A inverse, which is a row vector, every entry of that row vector, every one of those n entries in that row vector is basically going to be a strictly proper transfer function, strictly proper rational function, right. Now when you are post multiplying it by this B, you are again taking a linear combination of such strictly proper transfer functions or rational functions, and the resultant, the C times Si minus A inverse B, is then again bound to be at most of relative degree 1, yeah, or at least of relative degree 1, I am sorry, it can at most be of relative degree full n, yeah, but the relative degree at least has to be 1, yeah. So therefore the overall numerator polynomial must have a degree less than the denominator unless you had added some d, yeah. When you add some d to this, so for example when you add some d to this, now if suppose this d wasn't 0, then you see this d times this cubed, this cubic polynomial would get added to this, and therefore it would become strictly proper. So what am I saying essentially through all of this discussion in this long winded fashion, yeah, maybe I have taken up a bit more time on this, but what I am trying to say is very crucial and you have to remember this, okay. What I am saying is that given that I am allowed to represent the state space system in this form, x dot is equal to ax plus bu, y is equal to cx plus du, the transfer function that I can get out of the state space system can at most be biproper only when I use this feed forward term in the form of d. If I do not use that, it is going to be only a strictly proper transfer function. In summary, only strictly proper transfer functions or even up to biproper transfer functions can have state space realizations. So if someone gives you an improper transfer function and asks you to give a state space realization, you will say sorry, I can't help it, it does not have a standard state space realization. Now think of the PID controller. There is one pole at the origin and there are two zeros, right. So it is an improper transfer function. So a PID controller has no transfer, no state space realization, right. And because much of modern control theory has to do with state space and we like state space realizable controllers, right. All our problems are formulated as controllers given in their state space form. So the plant is given in its state space form, just like in the earlier case in the classical method we had GC and GS and CS, right. So GS was a transfer function, CS was a transfer function. Here in modern control theory in the general case we have the plant given as a state space realization and the controller that we want to design must also have a state space realization. So that is why we generally do not go for PID controllers in their rudimentary form, because they cannot be realized using state space realization for the simple reason that they are not strictly proper or biproper, they are just improper. Okay, so not just PID controllers, any time someone asks you to realize an improper transfer function using state space, you shouldn't even try, you should immediately say nothing doing, can't be done, it's impossible, okay. So that's an explanation that had been long time pending. I had promised this, so I thought I'll make good on the promise now. Okay, so now let's get back to this problem on hand. We've already warmed up a bit and we've seen how to get this transfer function from this ABCD matrices. So let's take a second example now. So the second example here would be Si minus A given by S minus 1 0 0 S plus 1 minus 1 0 0 S plus 3, right. So then this inverse is going to be this inverse. So let me try to find out the determinant of Si minus A. Yeah. So this determinant of Si minus A in this case will be pretty simple, because it is a triangular matrix. You can check that it is going to be nothing but just the product of these 3 terms, okay. So anyway, let me not skip that. It is a fact that if you have a triangular matrix, upper triangular or lower triangular, in this case it is upper triangular. So whether upper triangular or lower triangular, the determinant of a triangular matrix is just going to be the product of the diagonal entries. Yeah, in that sense it behaves, its determinant is like that of a diagonal matrix. So in a diagonal matrix also we know that the determinant is just the product of the diagonal entries. In a triangular matrix also the same thing holds, right. Okay. So in this case you can check also that S times this and this 0 times minus 1 gives you 0, and then you expand by this minus 1 and you see that it is all 0. So the determinant is pretty straightforward here, S plus 3. Now we have to find this adjugate. Yeah. So what we need to do is this adjugate of Si minus A. Yeah. So what is this adjugate going to be? So for the first term it is going to be just S plus 1 into S plus 3. So let me write that down, S plus 1 into S plus 3. For the second term it is probably going to be 0, for the third term also it is going to be 0, lovely. So we are basically, have a very nice structure to this, right. Yeah. You will see that, for triangular matrices it is actually easier to get the inverse. Yeah. I do not want to use that result, I do not want to invoke any results. So I am just going to do it like the good old fashioned way, hard work, yeah, because I do not want to burden you with too many facts along the way, which I am not going to prove in this class. So better not use such facts. So what about this 0? Yeah, this we found 0, this also, yeah, you can check that this is going to be 0. So of course we have to take the transpose of the matrix of cofactors. Yeah. What about the, hang on. So this is basically the second column. What about the last entry, this diagonal entry? So this is going to be S into S plus 1. Yeah, right. So this is going to be S into S plus 1. Great. What about this entry? So I am going to exclude the second column and the third row. So this is going to be minus S, but of course the sign will, I believe the sign should change, sign should flip, so it should be a plus S. Yeah. And then this entry, so that is going to be just a 1, and the sign does not need to flip. Yeah, it is going to be 1. I hope I am not making any calculation mistakes, any silly mistakes here. Yeah, so this is going to be this first column and the second row taken out. So it is going to be minus of S plus 3, but because there is going to be a sign flip, so it is going to be plus S plus 3. It is going to be S plus 3, and finally the middle term, which is when I take out the second row and second column. So it is going to be S into S plus 3 with no sign change, of course. It is going to be S into S plus 3 transpose. So that overall transpose of this, so let me write that down, S plus 1 into S plus 3, 0, 0, then S plus 3, S into S plus 3 and 0, and finally 1 S, S into S plus 1. So you see that a triangular matrix has its inverse also triangular. Yeah. So this is basically the adjugate. Of course now if I want to find out Si minus A inverse, then I have to also divide by the determinant, which is S into S plus 1 into S plus 3, I believe, right. So now what have I got to hit it with? I have got to hit it with this 1 0 0 on the left and 0 1 1 on the right. So let me just hit it with this C times Si minus A inverse B. So 1 0 0 on the left means I am going to pick out the first row. So this time I am going to do it quickly. Yeah, the C matrix is convenient for me. The B matrix unfortunately takes the sum of the second and the third column. So let me not do that quickly. Yeah, let me retain the B, but because the C is of a convenient structure, just picking out the first row of Si minus A inverse, let me just do the same. s plus 3 and 1. Of course, the determinant has to be there. So, this is s into s plus 1 into s plus 3 times 0 1 1. So, 0 1 1 means I have got to sum this. Yeah. So, what happens if I take the sum of this? Let me see. I hope this is not a mistake that I am making. You have to correct me if I am making a mistake, or am I? Let me see. Let me see if the calculations are correct. So, this is s plus 1 into s plus 3, this is the minus sign with 0, this is with a 0, with 0, 0, yeah, so this takes it out, this, yeah, okay. So, what about this? What I am worried about is this, probably this 1, am I making a mistake here? Let me check out this entry here. Yeah, it is a minus 1, it is a 1. Okay, just let me check the problem if I have copied it correctly. Yeah, let me see. Okay, seems like I might have done it correctly, in which case you just check the calculations. I am not sure if the calculations are all spot on, but this is going to be s plus 3 plus 1. So, I am not sure about whether this plus 1 sign, I have missed some sign here while copying the problem from some place. So, might be my bad, might be I am making a mistake here somewhere. Nonetheless, so by my calculation here, you please check this calculation and verify. By my calculation, this comes to be s plus 4 into s plus divided by s into s plus 1 into s plus 3. Yeah. So, that is what this transfer function turns out to be. Okay. So, we have done 2 examples, and already you have seen, thankfully it was a humbling experience for me that I could have also maybe made a mistake. Yeah. So, you have to do a lot of practice with this sort of problems, so as not to make these sign mistakes here and there, right, especially the computation of this adjugate. Yeah, this involves you have to be, this implies that you have to be pretty cautious. Yeah, I just still want to be sure that I am not making a mistake here, because while changing from one slide to the other, I might be goofing up the calculations. Let me check. S minus 1 0. Yeah, so this 0, if I take this out, so what about the adjugate of this? Yeah, so let me check. No, I seem to be doing fine, I think. I think there isn't any mistake here in this one, but anyway, please be sure that you check this calculation. All right. Yeah, because maybe when I was calculating it back while verifying, I had got s minus 2, s plus 2 somehow. Yeah, so I was worried maybe I made a mistake then. Who knows? I might have done it correctly right now. So the s plus 3 minus 1 maybe I had done somehow. I don't know. So please check. Anyway, the point of this exercise was to show you that there is a way to get from this transfer function, from this state space realization to this transfer function, and we have now got enough practice of doing that. We are now kind of familiar with how to go about this from one way to the other. Now, before we proceed further, in order that you might not get this impression that, well, there is something sacrosanct about those phase variable method and that drawing up that circuit diagram, that block diagram, those 2 methods. So here is yet another method which you might be able to relate a little more with. So suppose you have a transfer function which is given in the form, say, product of s minus zi upon product of s minus pi or pj. Yeah. So j goes from 1 to n, I goes from 1 to m. Okay, and pj and zi are all real numbers. All right. Suppose you have something like this. Yeah, all simple. So then you know that this can be expanded, yeah, in partial fractions in the form summation gk, k going from 1 to n, gk upon s minus pk. Yeah, so k is just a running variable, whether you choose j or k really doesn't matter. So I am just trying to distinguish this g from this z and p, so I just called it gk. You can also choose gj, whatever you like, doesn't matter. Right. So now, where of course this gk, these are also real numbers. Now this gives us a very ready-made, sort of a straightforward way to kind of implement a state space realization for this system. How so? So notice that this gs is equal to nothing but ys upon us is equal to summation gk upon s minus pk. Yeah, right. So then we can write that ys is equal to summation gkus upon s minus pk. But what is that going to tell us? Yeah, what is this? What is the realization of gk upon s minus pk? Or rather, let me take a number. Let me take the first one of such fellows. So let me take g1 upon s minus p1. Yeah. So I put it to you that you check that if I use this block diagram or this sort of a realization for this system. Yeah. So let's say you have this integrator here, and let's say this is the summer. So I know I have represented this sometimes as a cross, sometimes as a plus. Yeah, it really doesn't matter. It's summer after all. So as I said, we are only allowed to use summers and gains and integrators. Yeah, we are only allowed to use op amps in those three forms. Yeah. So you now see that I can readily call this as my u of s, big U, and this as my y of s. Yeah, why? Because this integration is nothing but 1 by s, no? So if I now want to write this transfer function down, this is actually as good a realization, as good an analog computer realization of this transfer function as any, right? So this gives me an idea. What if instead of placing that bank of integrator in cascade like we had done earlier, what if I put them in parallel? Yeah. So here's the idea. If you have a transfer function expressible in this form, yeah, why don't I do the following? So let me see, instead of putting the integrators in cascade, let me put the integrators in parallel like this. Yeah, and then let me just pull this out from here. So this is, let's say, my y1. So you see, then this I can call as my summation yk, where this term is itself, the entire term is basically yk. So then y is equal to summation yk. So basically what I am going to do is I am going to take all those yk fellows. So if this is y1, this is y2 dot 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 till let's say yn, yeah, and I am going to sum them up at the end, and I will have my y, right. So then why not use the same idea? I have this single channel of input because it's a seesaw system, this single input coming in here, yeah, let it pass through say G1 here, say G2 here, like so on and so forth likewise, and finally let this final fellow, this pass through Gn here, and then let there be this summer depicted by a cross or a sum, whatever you like, yeah. So I have this block P1 like so, I have this block P2. So again I am not violating any of the conditions, I have only used gains, integrators and summers to realize this. So this is as legitimate a realization as any. So this is Pn, in fact it will come with a minus sign. so maybe I should be a little cautious. No, in fact it won't come with a minus sign because I have already put in S minus P1. Yeah, so it will come in with a P1. Sorry about that. So it will come in with a P1. This is P2 and this is Pn. That's correct. So then what I do is I tap in all of these together like this at a summer again. Yeah. So these are all summed together and this gives me my y. But what is so curious or interesting about this? If I now use the same notion as what I started with, that is the physical notion, that call the output of each such integrator as a state. So then let me call this x1, let me call this x2, let me call this xn. Then what do I have? You see, for the first integrator I can write then that x1 dot, which is nothing but the variable that is here, this is x1 dot, is nothing but g1 times u plus p1 times x1. Likewise, I can write xn dot is equal to gn times u plus pn times xn. So written in the, let me go to the next slide, written in the compact notation, what is this going to look like? x1 dot, x2 dot, like this, dot 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 till xn dot. What I can then write this as is this, x1, x2 dot 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 till xn. Yeah, this is going to be just nothing but, you see, p1, p2 in the diagonals. So this is a completely decoupled system of differential equations, no? In the sense that if I have written this, yeah, I can treat each of them. So this x1's differential equation involves only x1. This is just tantamount to solving. Yeah, so this actually leads us to the next step, which I hadn't intended on discussing today, but you can't help but notice this and can't help but take a flight of fancy and extrapolate this to apply it to a solution of the state space system. Yeah, so that's why I'm just putting that idea, planting that idea in your minds even at this stage, though we haven't approached that yet. Yeah, but you see here, this is nothing but you can, when solving for x1, you can forget about x2, x3 and all the other states till xn. The same holds for everyone. So this is a completely decoupled system. Yeah, this is like a kind of like a dream come true from the solver's perspective. Yeah, may not be such an easily realizable system, because if those x1, x2 that we have defined in this fashion, if they are not really very convenient physical parameters to handle, we may not be able to actually realize this on the analog computer. So those are again issues of implementation. We will come to those questions later. But now, for now, you can at least see that this is how it turns out. And what about the B matrix? Well, the B matrix just looks G1, G2 like this till Gn times U. What about the Y matrix? Y, the C matrix? Well, it's nothing but the sum of all these fellows, right? It's nothing but, so Y, let me write here, Y is equal to nothing but x1 plus x2 plus dot 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 till xn. Why? Because each one of those x1s, remember, they are your y1s in the, like we showed in the previous slide, right? This is how we are defining the states. So this is just 1, 1, 1, 1 like this, 1 till we have x1, x2 dot 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 till xn. Okay, so it seems all very good, very hunky-dory, but if you've been paying attention in your Laplace transforms chapter earlier when we were discussing long time back towards the beginning of this course sometime, you would immediately be faced with a couple of niggling questions. Yeah, they should be sort of bothering you a bit at this point. First question, well, you've taken a very specific structure of this transfer function. What if, say for instance, I have a transfer function that looks like s plus 1 upon s plus 2 into s plus 3 into s plus 4 squared. Yeah, in that case, you see, if you expand this, you will have something like g1 upon s plus 2 plus g2 upon s plus 3 plus g3 upon s plus 4 plus G4 upon S plus 4 squared. Yeah. Now, can you still go about and realize it in this diagonal form that we have seen so far? Yeah, in the previous slide. Yeah. Obviously, you know, a moment's thought will tell you there's no way you're going to be able to realize it in this diagonal form. Why? Because now you don't have just first order terms like this which can be realized conveniently in the form of an integrator like this and feedback structure like this and then summed over here like so. Yeah, so this is the standard block, but this block, yeah, does not fit. Yeah, this block is like the defect. So if you have repeated poles in the transfer function, apparently your hopes of diagonalization seem to be dashed, right? So it seems like there's nothing we can do in that case, right? Well, maybe we cannot diagonalize, but not all hope is lost, you see. So you can still, you know, get as close to the diagonal block as possible. How? So let's say you have you want to realize this, say I take a sample transfer function, say 5 upon S plus 2 cubed. Yeah. So if I want to realize this, so I necessarily also have some 7 upon S plus 2 squared plus say 6 upon S plus 2, yeah, if this is my GS. Alright, suppose this is my GS. Now clearly I can at most realize this block in the standard fashion, so let me go ahead and do that. Yeah, so let me go ahead, but I also know that I have to realize a third degree transfer function, so I need 3 integrators, but maybe I cannot put them all in parallel now, so maybe I will have to put them in series somehow, but okay, at least so this is only one part, remember, this is only one part which is concerned with the repeated poles. There may be several other terms as well. For example, there may be 10 upon S plus 2 plus 25 upon S plus 3 plus 37 upon S plus 25 plus so on and so forth, you know, there may be many other terms. So we are only stuck at this point where we encounter these repeated poles. The other fellows we can conveniently proceed in the same fashion analogous to this, right, in this fashion. So the moment we encounter repeated poles like this repeated poles at minus 2 in, for example, in this case, that is what creates this problem. So we wonder, like, is there a way to bypass this? Yeah, and we will see very easily this can be bypassed if we just compromise a bit. So now, for example, if this is, let's say these are all the terms that are there. So what is the degree of this transfer function? This is an S plus 2 cubed. So I can readily predict that the denominator polynomial of this GS will look something like S plus, so this is, let's say, S plus 4, not S plus 2. So S plus 4 into S plus 3 into S plus 25 into S plus 2 whole cube. That is the LCM, the least common multiple of all these denominators. Yeah, so that is the LCM. So this is going to be my denominator polynomial for GS, yeah, and some numerator sitting over here depending on how these are weighted. So this is my GS, yeah. So now you see that I have this 6th degree differential equation obviously, so I will need 6 integrators. So 3 of the integrators I have used up for this block, and this block, and now for these remaining 3 blocks I have to use 3 more integrators, but the problem is that because this is not purely diagonalizable, because this is not appearing in the standard form like earlier, I may not be able to use those other remaining 3 integrators in the parallel form. So let me just do what I can with the first 3 integrators. So the first 3 integrators here I have this, let's say minus, let's say I have this minus 4, yeah, minus 4. yeah, here I have this minus 4, then the second integrator I have in cascade, so I have this summer here, right. So I am going to sum this here, I am going to sum this here. So here I have this minus 3, yeah, like this, like this. So these are all again some constants, you can fill it up from these coefficients, right. So s plus 4, it goes with 10, this one will probably be, yeah, 25 according to what I have written here. And then this third integrator, I am just going to write, so this is going to be my y, this third integrator I am going to pull out, so it is going to have gain 37 for instance, yeah, and then this summer, so this summer here, and this is minus 25, yeah. But now once I have done this, so this is all my u's are going through this, yeah. But now I have to also, now I am faced with the problem of realizing this part which I marked in this blue box. How am I going to do that? So this is the question that is facing me. The first thing I observe is I have to compromise, I cannot do this in the usual diagonal form. So what do I do? So let me see, can I put them in series like this? Maybe, and then try and realize this, then try and sort of figure this out, yeah. So how am I going to do this in series like this, okay. So you first see this, let us say I pass it through 5 here, yeah, and then this goes here through this first integrator, second integrator, third integrator, yeah, and then I just realize this, sorry, I think I do not have space, so maybe let me just, let me continue this part of this figure in the next slide. So in the next slide I am going to continue just this part of the figure, you realize what I am trying to do here, right. So let me go to the next slide here. So let me see the other remaining blocks, that is these 3 blocks have been well taken care of. Now what I need to do is I need to put this particular block, right. So first let me just try this out. So this is 1 by s plus 2, 1 by s plus 2, yeah, and 1 by s plus 2, okay, that is my one. So then if I pass an input signal through say 5 and pass it through this, yeah, so this is already giving me the realization of this this first term here, okay. How about the second term? So for the second term, what I then can do is, yeah, what I can do is I need not pass it through, I need not pass it through all the 3 integrators. So let me just pull this out from here and let me remove this here and add a summer here, yeah, again the sign of the summer, okay. So I need a 7 because that was what the gain was, yeah. So now you notice that I have that same input channel, this u. So what is happening? 5 times u is passing through this, all 3 blocks, right. 7 times u is passing through only 2 of those blocks. Now you can easily guess what I am going to do next. So I am going to just introduce another summer here or adder here, and I am going to say that what was the third term? 6, yeah. So 6 times this is going to pass through this one integrator. So you are convinced, right, that this is a good enough realization, this is a good enough realization of at least y bar, where y bar is going to be, let me write here, so y bar is going to be this 5 by s plus 2 cube plus 7 by s plus 2 squared plus 6 by s plus 2 whole of this times u, yeah. The entire y also contains responses due to these remaining 3 which are perfectly diagonalizable, but this at least yeah, can be realized in this fashion. Once I have done this, it is just standard process to check. I just can sort of realize this in the following manner: 7, 5, 6, and this S, of course I can pass it through a bank of integrator, and just call it this here. So this is a -2 like this, yeah, this is a summer here. So again there is a summer here, and then again I put this another bank of this integrator with this yeah, I have this -2 here, right. So that is how I put 3 of them in cascade, and then again I have another summer here where I add this, and then I have this last realization which is going to be this -2 here, yeah. So this is going to give me my y bar from the U. So I have actually done it, I have actually again used up only op amps as gains and summers and integrators, and I have realized this. Of course the compromise here is that I have not really realized it in the perfect diagonal form, because I simply cannot. So how does this help this part at least? So the remaining part of the transfer function, that state space realization, isn't very interesting. So let me just talk about the realization. Let us ignore this part, because this part is just diagonal. I can totally see, yeah, how this is going to behave. So let me just talk about how this part, the state space realization, looks like, yeah. So let me call this x1, this is an x1 dot, this is x2, this is an x2 dot, and this is x3, and this is then x3 dot. So I have x1 dot is equal to -2x1 plus 6u, or rather let me reverse the order here. Let me call this as x3, this as x2, and this as x1. Yeah, I mean in a moment you will see why this I prefer this. It is just a labeling after all. So x3 dot is equal to -2x3 plus 6u. What is x2 dot? X2 dot, if you see here, x2 dot is going to be -2x2 what is coming in here, plus 7u plus x1, and what is x1 dot? X1 dot is, well, -2x1 plus 5u, yeah, okay, hang on, I think I have missed this x3 dot, I have missed this, yeah, there was an x2 as well here, right. Okay, maybe I had taken the order right the first time around. So hang on, just bear with me a while and we will be done very shortly. Yeah, okay. So you just take this as x1, this is x1 dot x2, and this is x3. So this is x3, this is x3 dot. Okay, yeah, fine. Let's go back to what we were doing earlier. So x1 is equal to, x1 dot is equal to -2x1 plus 6u plus x2, yeah, because this x2 is also coming in, remember, x2 plus 6u minus 2x1. x2 dot is equal to -2x2, and this channel, what is coming through this channel, x3 plus 7 plus x3 plus 7u, and x3 dot, which is just this channel, nothing is coming in from the others except that 5u. So we have -2x3 plus 5u. So if I just realize these three states, yeah, and forget about that, then what I have is not exactly a diagonal realization, but you see it's close to a diagonal one. So x1 dot, x2 dot, x3 dot is equal to minus 2, 1, 0, 0, minus 2, 1 and 0, 0, minus 2, x1 plus of course 6, 7, 5 u, and y is given by x1 which is 1, 0, 0, x1, x2, x3. Yeah. The beautiful thing about this is that this form of the matrix is called the Jordan canonical form. So it is the closest you can get to a diagonal form. If you cannot diagonalize a matrix, then the best you can do, if you go through a detailed course on linear algebra, you will find that the next best thing to a diagonal form is this Jordan canonical form, which we have here, right?
Oh, sorry, that shouldn't be x1, that's just my bad, that should be x, that's the entire vector of the states, right? So let me write x1, x2, x3, the entire state vector here, not just x1, that was just a careless mistake on my part. So this is x1, x2, x3.
So now if you look at the overall transfer function or overall matrix, you can augment this. So you will see that this last 3 by 3 block is this minus 2, 1, 0, 0, minus 2, 1, 0, 0, minus 2, yeah, and the remaining blocks for example will be this minus 4, minus 3, minus 25. So minus 4, minus 3, minus 25, yeah, 0, 0, 0, so on. So these are all going to be zeros and all zeros here. So this is what your A matrix is going to look like. So although it is not exactly diagonal, it is the closest you can get to diagonal in case of such repeated poles in the transfer function, right. So that is another convenient form of the state space representation. The next question we are going to answer in the next lecture, we are going to start off there, is what if we have complex poles, right. So we saw that in the transfer function domain we could have had complex poles, and complex poles, remember, do not lend themselves to factorization over real numbers in the form that if you have this, for example, omega n squared upon s squared plus 2 zeta omega n s plus omega n squared and zeta less than unity omega n greater than 0, if you have this, yeah, then you cannot factorize this in the form of 1 by s plus p1 into s plus p2, where p1 and p2 are real numbers. So this does not work. You cannot go from this transfer function to this, yeah, and if you cannot go to this transfer function, you cannot factorize it like this, then you cannot split it up into diagonal blocks even if the roots are not equal. So we earlier saw that one defect is even if roots are real, if there are repeated poles, the poles are real but repeated in the transfer function, then you cannot diagonalize it. So then you go for this sort of a combination of the parallel and series, right, whereby we get the Jordan form. But now the other problem is, even if your poles are not repeated but if they are complex, you have to after all realize this using some real parameters. You cannot realize complex numbers using real parameters, no, real parameters like your resistances, inductors, capacitors, those are real variables, right. So you cannot split it up into this sort of a factorization like this and then realize it. So then what do? Do you just give up your hopes of diagonalizing such blocks, or at least in the block sense, like we did this Jordan block form here, not exactly diagonal but at least block diagonal, and this has beauty, right. We just took the last example where we saw the triangular matrices, yeah, they are relatively easier to handle, right. We will also see when we solve them that triangular systems are easier to handle. So at least can we get a block diagonal form in this case in the real over the real numbers, because if we can, then there is hope that we might be able to realize this in a simple looking block rather than this whole complicated looking structure, okay. So that is what we are going to see in the next lecture right at the beginning. Thank you.